In number 16, we have a balloon that is floating on the ocean. And underneath the balloon, there is a block of rubber that is 457 milliliters in volume. And we were told that the volume of the balloon was 1.93 liters, and that 1 atmosphere of water equals 10.3 meters of water equals 1 atmosphere. So this is the only clue we have. Now, obviously at this point, it's very buoyant. So at this point, we know that the buoyant force is much greater than the weight, and so it stays up on top. But if we push a balloon deeper and deeper in the ocean, then the pressure is going to get bigger, so the volume of the balloon is going to get smaller. Eventually, there should be a point where the buoyant force is equal to the weight, and if we pull any farther down from there, then that means the buoyant force will be smaller than the weight, and it will sink forever. So what we want to do really is find out this part. What is this? And then if we go any farther than that, it's going to sink. Does this make sense? So first we got to figure out, again, if we're at equilibrium there, then again we know that if the buoyant force is equal to the weight, then we know that the V rho G is equal to the mg. So what's on both sides? G. So we don't really care about that. And of course V rho is equal to mass. So basically we're going to have the mass of the water has to equal the mass of the rubber and the balloon. And so that's always going to be true whenever you're floating. Whenever you're floating, you're going to displace an equal mass of whatever fluid you're in. In this case, it's going to be seawater. So we have to do a couple conversions so that we have masses correct. So first thing we want to do is, again, we know that density is equal to mass over volume. So if we're looking for the mass, I'm going to bring the volume over here. And so if we have this volume, 457 milliliters times the density of seawater, that's going to tell me the volume of, I'm sorry, I'm on drugs. Here I'm doing step 2 instead of step 1. Here it's rubber, so we want the density of rubber, that would be 1.34. And then the balloon, we have, I'm going to put this in milliliters so it matches. So we're going to have 1,930 milliliters for the balloon. And we're going to have the density of what's in the balloon? Say air. Air. Thanks. So we're going to get this much mass. So 457. 4.34. So we're going to have 612.38 grams of rubber. And we're going to have 2.28 grams of air. So if we have these underwater, we need to displace what mass of seawater? Do that. So 8 and 8 make 16. 24. Does that make sense? So the total mass of the other two objects is going to equal the mass of the water that we have to displace. So now that we have a mass of water, we need to figure out the volume of water. So again, if density equals mass over volume, and these two will trade places. Volume is going to equal mass over density. So we're going to take that mass and we're just going to divide by the density of seawater this time. And we get 603 milliliters.
Where did it go? 1.02.
It came from the chart on what's the density of seawater. Okay, so since we are in seawater here, we're going to use the density of seawater there and find out that we need to displace 603 milliliters of ocean water. Now, which of these two masses or volumes are not going to change? The balloons or the rubber? The rubber is not going to change. The balloon's going to be able to be compressed, but the rubber's not. So if we subtract out the 457 milliliters that's already the rubber, then we'll figure out how much is left for the air. So 603 minus 457. So we need to shrink that balloon down to 146 milliliters, and anything less than that is going to make it sink. Now, right now it's 1,930 milliliters. I got to shrink that all the way down to 146 milliliters, so I'm going to have to do quite a bit of pushing. What's the relationship between pressure and volume that you understand with gases?
Inverse.
They are inverse. Ideally, in chemistry class, you learned gas laws.
Pressure increases, volume decreases.
Yeah, that was Boyle's law, right? So with Boyle's law, we had P1 V1 equals P2 V2. Now, when the balloon is sitting right at sea level, it has how much pressure on it? 1 atmosphere, caused by the atmosphere, right? So we can say we have 1 atmosphere of volume, of pressure with a volume of 1,930 milliliters of air. And then we want to get it down to an unknown pressure with our target volume of 146. Does that make sense? So now I just clearly need to move 146 down over here. And that gives me 13.2. So I need 13.2 atmospheres of pressure to push on it that hard. Now here's where people make a lot of mistakes. So I've got 13.2 atmospheres of pressure. You think that I need 13.2 atmospheres of pressure caused by the water, but you don't. How much pressure do we need caused by the water? 12.2 atmospheres, because we already have the 1 atmosphere caused by the air. So the air is still pushing on you even when you're underwater. You don't go underwater a little bit and then say, oh, the pressure got lighter. You've got more, so it's always an increase. So we have to subtract out the 1 atmosphere caused by the air. So that gives us 12.2 atmospheres have to be done by the water. So if we have 12.2 atmospheres, and I give you the handy dandy conversion factor of 1 atmosphere is equal to how many meters of water? 10.3. That means we need to sink that puppy 126 meters down. And right there we would hit equilibrium. So if we're a little above that, the balloon starts to swell a little bit more, and it's going to swell more and more and more the higher up it goes, and it's going to pop up to the surface. Or if we shrink it, if we sink it a little farther, it shrinks a little bit more, and now the weight is bigger than the buoyant force, and it sinks, and the volume of the balloon gets smaller and smaller, and it just keeps sinking faster and faster. Or you lose it forever. Nice.